in the last lecture, we talked about the simulator setting or generative model. I think the simulator setting, the most important thing is we have a simulator, so we can query any state action and step each pair, and then we get a next states and the reward as a feedback. So we talk about we spend most time focus on the first algorithm called value iteration. In this course, we will just, as a shortage, call it VI. And at the very end of the last lecture, we talk about another algorithm called Q-learning. The major difference is in the value iteration, we kind of like do the batch update. Well, in the Q-learning, we kind of like we're trying to do the online update or like incremental update. This is like we collect all the data and we do one pass of update. This is like as long as we collect one data, we do a new update to it. So today we will be a little bit more concrete on the Q-learning algorithm and we will talk about the results of what we can get for Q-learning. So we'll talk about the formal algorithm. So Q-learning algorithm need to input a sequence. As we said last time, it's like which is like the learning rate, which is a sequence of alpha t. That is t from 1 to infinity. Essentially, alpha t is trade-off like how many fractions we trust the previous Q value, that is 1 minus alpha t fraction, and alpha t times the new update. So this is, you can think this is like sequence of learning rate. And we will talk about how we choose this learning rate at the very end. So in terms of the main algorithm, we first initialize with QH 0 SA. You can initialize to be 0, or actually you can initialize to be anything for any SAH. That is, I will just initially assign some value to the Q value function. Then Q-learning algorithm iteratively doing the following. That is for t from 1 to and then inside the loop, we say for h equal to 1 to capital H. For all state action in this step, we will basically query the simulator. This SAH. And the important thing is now we only get one samples of the next states. And then we will do the following update. That is QH T SA is equal to 1 minus alpha t. This is like the same update we said the last time. That is 1 minus alpha t times the previous Q value plus alpha t times the new update. Okay, this is for all state action pair. Then we will also say for all state in this step, just do VHTS equal to max A of QHTS SA. Okay. So the indent is the same. Like so, this for loop is inside the to for loop here. So what we essentially have is like the for algorithm, which the key step is what we talked about last time, where we do the incremental updates, that we will basically assign Q value to be 1 minus alpha fraction of the previous Q value plus the alpha fraction of the new update. And the remaining thing is just after we get in a Q value, we will calculate the V value that's equal to the max of the Q value taking over action. So you can think this algorithm kind of combine this sample next states with the update together. Well, instead of like VI, value iteration, we have a first phase that is collecting data, and then second phase like doing the updates. So I want to make a few comments about the algorithm. The first important thing is in this algorithm, we no longer explicitly constructed the transition. So this is some difference, I think, in the classical literature. It calls model-based versus model-free. I think this separation is, in some sense, a bit like in the high level. It's not like a very mathematical. But basically, like the conceptual idea is like saying this approach is like you construct a model. Like construct a model means you construct what is the p hat, what is the reward. Like you directly estimate what is transition, what is the reward. And this model free means you don't construct the model. So if you're using this definition, you can think this value iteration algorithm is actually a model-based algorithm, because in the first phase, we can directly construct what is transition probability, while this Q-learning algorithm, we never construct what is transition. And the transition, like the learning transition part is kind of like implicit in this incremental update here. So we don't directly construct the model. And this is like a model-free algorithm. So Q-learning is model-free. So if you're saying like this seems like too artificial, like what is the mathematical difference between those two styles of algorithm? We can actually use the space complexity to differentiate these two classes of algorithm. So in the space complexity, in terms of space complexity, that is how many digits you need to store for each algorithm. Like the value iteration algorithm, because we need to estimate the transition, so it's roughly at least order h s squared a. Because at each step, we will estimate directly construct a transition and use transition to do like this matrix vector multiplication. Well, in the Q-learning, we only use HSA space. Okay. The reason is now all we need to store in the algorithm is just this Q value. Well, Q value only has the SAH different numbers in the table. So you can think this is sublinear in the model size. And by model size, I mean like the number of parameters you have. This is like precisely the number of parameter, roughly the number of parameter up to some constant. Well, this is like sublinear in the number of parameters. So that's why it's called like model free. The second point I want to comment out is I want to say the sample complexity. Of Q-learning and VI. So in terms of value iteration, we already talk about the sample complexity of value iteration in the last lecture, which is O tilde of h to the fourth SA over epsilon square. In terms of Q-learning, you can do a similar analysis. We will give a little bit sketch, like immediately. But the result is you can essentially prove the sample complexity is something like this. It's h to the fifth of SA over epsilon square. So we'll not talk about the formal proof about this result, but I just want to say Q-learning can essentially achieve a very similar result to value iteration, but with slightly worse. H dependency. So in terms of sample-wise, actually, by doing this incremental update, you can more or less imagine this is not as efficient as like a previous value iteration algorithm, which you kind of collect all the data and use all the data simultaneously. While here, you kind of you use the data in the beginning and then you throw data out, and then you collect new data. So in that sense, like you don't like utilize the power of like each sample to its maximum. So that's why it has a like slightly worse H dependency. And we'll also talk about the intuition why it has slightly worse. But I just want to also say you can think this is as a trade-off. Like I kind of allow slightly worse sample complexity, but I kind of have better space complexity where we talk about it. And we will actually also have better computation in the online setting. So we haven't talked about the online setting yet, but we will talk about it today. And so far we talk about only simulator setting. In a simulator setting, value iteration kind of like collect the data in the very beginning, and then only do one pass of dynamic programming. So this is computation is fine. But in the online setting, value iteration need to do multiple passes of Bellman optimality equation, and in that case, it's very slow. So you can essentially think every time Q-learning need to do one incremental updates, this VI need to do like whole pass of like a dynamic programming. So that's why in the online setting, actually computation of Q-learning is also better. Okay. So I guess I will not formally like go to all the proof about the Q-learning why it can also achieve like the sample complexity. We will just point out some key steps to let you know like how this thing happens. So in order to do analysis for the Q-learning, I think the most important thing is we look at this key steps we have. So let's just copy the key update, which is QTH SA equal to 1 minus alpha t QH t minus 1 SA plus alpha t RH SA and plus VH minus 1, VH plus 1, T minus 1 as ST prime. So we see this is like a previous Q value. And this is like the new update. At time t. Or at a iteration t. So this direct formula is a little bit difficult to analyze, but you can think one very straightforward way to analyze this update is you kind of like recursively expand it out. This Q value is again equal to 1 minus alpha t minus 1 fraction of QT minus 2, and plus this thing times alpha t minus 1 of the update at a t minus 1 step. So you can recursively expand this Q value out, and you can actually equivalently have another form of this Q value. You can return as something like this. RH SA plus summation of I from 1 to t gamma t I and VH plus 1 I minus 1 SI prime. Essentially, it's a weighted sum of all previous values, and like a previous value operates on like previous samples. So you can imagine like you just expanded this entire Q value out from t minus 1 to t minus 2, t minus 2 to t minus 3. So eventually everything happens in the first term kind of like goes away, and all you have is a bunch of summation of the second term. And the second term, and because all the alpha and this reward is the same, so reward summation together equal to 1. And while this thing is what remains, it's like a weighted sum of this value. And we will see, and by calculation, you can actually get that gamma iti is equal to alpha I times the product j equal to I plus 1 to t 1 minus alpha j. And this summation I from 0 to t gamma ti is equal to 1. Okay. So what I'm saying is just starting from this recursive equation, you can prove, you can do some calculation essentially by expanding out this previous Q value, and then eventually you're getting this. It can be viewed as a weighted sum of all the updates. And while the weights, we can do the calculation of weights is in this way, and the weights sum to 1. Okay. So we will compare this to the value iteration. Where we know the value iteration, we're doing the following updates on the Bellman optimality equation. That the Q value is equal to R plus P hat, which is our estimate, and then V plus 1 hat SA. And you can essentially expand out what is the definition of P hat, which is using the empirical frequency to estimate the transition probability, which is equal to RHSA plus summation I from 1 to n and 1 over n VH plus 1 hat SI prime. So this is like the value iteration. So we notice if we compare those two updated equations, there are like two differences, I think. So one difference is now we're doing like a weighted sum. The first difference we're doing, okay, let's see. This is like this is like summation with equal weight, but here like we can potentially have like different ways. We can either favor in the later ones, favor in later updates, or we can either favor in the previous updates. Like basically we have the flexibility of choosing our learning rates, which can tune like what is the weights we put here. And the second difference is we actually note here, like this is just using V hat, which is our estimate of value after we're collecting all the data. But here is the value at ith iteration. So Q-learning uses value at previous iteration. So in that sense, this V hat is basically calculated after you collect all the data. So this V hat is reasonably accurate. Well, here the value is like used at the previous iteration. So you can think like the VH plus 1, for example. This is like the value you calculate at the first iterate. And in that case, you only observe one trajectory or one data. And in that kind of scenario, clearly, this is like not very accurate. So VH plus 1i is not accurate for small I. So this is where, like, in terms of Q-learning, we have a little bit more complexity we need to deal with. So we'll talk about the next thing is how we're going to choose gamma t, like how to choose our weights. So essentially, we have like two conflicting part we want to handle for this gamma t. The first one is we want to have gamma t to put more weights on values of later updates. This is because, as we said, the VH plus 1i is not very accurate for small I. So we essentially want the gamma to put more weights on the value with like at later iterations, so to reduce the bias. Okay. So ideally, for example, we just put a probability 1 or the weights 1 on the very last iterate, and in this way, like we have the smallest bias. However, we should not do that because the second thing is we want to gamma I to be spread out. We should not like focus all the weights on one single sample because single sample is like a statistical sample and it has a lot of like a noise. So we want the gamma t to be uniform in some sense. To reduce the variance. This is like the variance part. So basically, we can think the ideal choice would be something which we will put a lot of weights on the later updates, and so the previous iterates have smaller value, and later iterates have like higher weights. But on the other hand, we should not just focus on one update because it has a lot of noise. So we should still like make it relatively spread out. Any question about this, like a bias variance trade-off principle in this Q-value, Q-learning part? So now, like we have some like intuitive idea of how we choose gamma t, and then we talk about some specific value. So our baseline is we look at alpha t equal to 1 over t. This is one very simple way you can compute, and you can actually use our formula for gamma it, and you can compute the weights. Gamma t1 is actually equal to gamma t2 is always equal to gamma tt. And this is equal to 1 over t. So this corresponds to the uniform weights. That is, if I choose learning rate equal to 1 over t, we actually happens to be the uniform weights. And this is the part, essentially, we're very good at variance, but somehow we're not very good at dealing with bias. Actually, this rate does not give good. Good sample complexity because of bias. So as we said, we want to tune this a little bit towards favoring the later part of the updates. And by favoring later parts of the updates, that means we need to basically increase the learning rate. By increase the learning rate, that is, we kind of put more emphasis on the later updates than the previous Q value. So it turns out, theoretically, you can prove the learning rates which achieve this sample complexity is something like alpha t is equal to like h plus 1 over h plus t, which you can think is roughly in the order of h over t. This is like a better choice. So you can think high level is, and this is something like essentially you put more weights on the later iterations. So this is like roughly similar to like put relatively uniform weights. On the latest 1 over h fraction of data. And because we need to dealing with this bias variance trade-off, So that's why we essentially need to ignore to some extent, ignore the earlier part of the data. So that's why we're not that sample efficient. We essentially pay some additional H factor because we're not doing uniform weighting. We're doing some more aggressive weighting towards like later updates. This essentially is the reason why we have like slightly worse H dependence. But just remember, we still have like better space complexity and also the computation complexity. Computation complexity, I think we said in the similar setting, we cannot see it. But in the online setting later, we will actually see it. Online setting is in the exploration setting. I think the reason is because in the simulation setting, we essentially just collect all the data, and then we do one pass of planning, that is a Bellman optimality equation. Well, in the online setting, that is we can no longer sweep over all the state action. We actually will talk about immediately about like what is the setting. But the main takeaway is that when we do the value iteration, we actually need to collect one trajectories and then do one pass of Bellman optimality equation, and then collect one trajectories, then we do another pass of Bellman optimality equation. While in the Q-learning, we just collect one trajectory and do one pass of this incremental updates. So that's why you can do a lot faster than that value iteration. So I just want to before we move on to the next setting, we'll just do a slightly summary of the simulator setting. So specifically, we talk about the non-stationary transition case. Where by non-stationary, we mean we kind of like assume P1 is not necessarily equal to P2, is not necessarily equal to Pn. Okay. They can be equal, but we don't really require it to be equal. So it can be like different. And then we just talk about two algorithms. Essentially, we kind of already summarized there. We talk about the model-based. That is VI, and model-free, that is secure learning, where the most important guarantees we talk about is the sample complexity, which this one is O tilde, h to the fourth, SA over epsilon square. And the space, this is h s squared. Well, in terms of Q-learning, our sample complexity is O tilde, h to the fifth, SA over epsilon squared. Slightly worse. And while the space, we can like save some space by doing model free, that we no longer suffer s squared dependency, we only pay s dependency. And we will also talk about later in the like lower bound session or fundamental limit, there's a lower bound. Or like information theoretical lower bound. Information theoretical lower bound basically says because by our assumption of the model, we kind of like assume each state, next state, and the reward are like randomly generated. So there's always the statistical like noise in it, and the algorithm in the worst case like cannot really tell which one is the optimal policy because of those noise. So that is, we will see like in the worst case, like essentially any algorithm in the worst case needs to pay at least this amount of samples to learn the optimal policy well. So we will discuss this topic after we talk about the exploration setting or online setting today. So this essentially says no algorithm can do better than this. In the worst case. So this more or less conclude that VI almost achieved we call it minimax optimal sample complexity. By almost means up to some log factor. Like here we have the O tilde here, while the lower bounds will prove in the class does not have the log factor. But more or less in this class, we don't really care about log factor, so we will just say VI kind of like already achieved our goal of getting it's the best algorithm in this setting in terms of sample complexity. Like you cannot beat value iteration in terms of sample complexity in the worst case. Okay, so any questions so far about the simulator setting? Now we will move on to talk about the next topic, which is the online reinforcement learning. Or we also call it exploration setting. So basically, we talk about this is like more challenging setting that we no longer assume the simulator. So first, what is the online reinforcement learning setting? So just remember how we're going to interact with the MDP. The protocol of interacting with MDP is like we have the S1, and we go to R1. We have A1, the first action, and both of them simultaneously determines the reward you receive at the first step, and both of them determines like what is transition probability go to the next states. Okay. Like something like this. So the protocol in the online reinforcement learning setting is we will just observe the initial states. And then for h equal to 1 to capital H, agent takes action AH, and then the environment transition to the next state, SH plus 1, and send the reward RH. And the most important thing here is in in the online reinforcement learning setting, we will just basically reset to initial states. And we only allow, like after we play the entire trajectory, then we can go back to the initial states, and then we can do everything again. So in the online reinforcement learning, it's like more challenging in the sense it's like basically we will play the entire trajectory. So this is like the biggest difference between the simulator and the online IL. Is that in a simulator, you can basically choose both state and action. Well, in the online reinforcement learning, you're essentially like playing a real game, or like you're kind of doing a robot. You always like reset to initial states. And essentially all you can do is you just choose the action sequence. You no longer have the freedom to choose the states. This is like the major difference. You can think this is like more or less, it's also how we play the game. Like when we die, we go back to the initial states and we play the game again. So this also like mostly like affect how we're gonna collect the data. So one very important thing is in a simulator setting, we can just basically use a very simple strategy to collect the data. That is, we will sweep over all state action pair. Essentially, in the value iteration algorithm, is we kind of query the simulator for all state action pair, and then we get next states, and this is basically done. And our data collection from there is like very good. However, in online reinforcement, we can no longer do that because we can no longer like just for free set to any states. Okay. So in this case, just simply like reach some states. By itself may not be an easy task. For example, imagine you're playing like Super Mario and some states is in like a last chapter, and by reaching there is already not very easy. Like you need to do some complicated strategy so that you can eventually go to the last chapter of the game. So one important question we will handle in the online reinforcement learning is how to efficiently collect data. In a sense, like we want to collect the informative data. Where basically in a simulator setting, as long as we sweep through all the state action, we're collecting informative data. Well, in the online reinforcement, this is no longer that clear. And we will actually give an example showing why this is actually a non-trivial question, or this is like an interesting question. So we'll talk about the failure of random exploration in MDP. Okay, so what is a random exploration? So the first idea to collect the data is here in a simulator setting, because we can choose all the state actions, so we just sweep through all the state action pair. Well, in the online reinforcement learning, although I cannot choose state, but like by random exploration, that means like basically every time I just choose action randomly, like every time when I take action. This means like at every step. So this would be some naive idea. I would try to see if the data we collected in this way is like a comprehensive, is like it will give me a lot of information. So it turns out this random exploration strategy in MDP is like highly ineffective. It may suffer from some like this is highly effective. This may suffer from some a to the power of h some complexity. So this thing might suffer something like that is exponential in the horizon. So basically, for anything that has a long horizon, like for example 20 or something, this entire method kind of like is really screwed. Like you cannot use this way to collect data very effectively. So we'll talk about why this is true. Like we basically just construct some hard instance, so that we show for this hard instance, this algorithm is like very bad. Okay, so to show this, we constructed a hard instance. Hard instance in our literature is actually pretty famous. A lot of later like hard instances like based on this. It's called combinatorial lock. By the way, I also want to emphasize this is like hard instance only for random exploration. So later we'll actually have better algorithms so that it can basically. This is no longer hard. Like we can basically solve this problem. So this is like different from this information theoretical lower bounds. This lower bound says like no algorithm can do better than this. But this lower bound essentially says this algorithm is not good, but other algorithm can be good. Okay. So we look at this combinatorial lock. Combinatorial lock is an MDP. It's a two-state MDP. And let's say with A actions. So the MDP is actually a deterministic MDP. Okay. We don't even need randomness to like essentially break this random exploration algorithm. So we look at the MDP only has two states. So at every step, we have like S0 and S1. Those are the two states. Okay. Maybe let's use superscript so that to make it different. This is not talking about step. This is like basically in the first step, I have two states, that's S0 and S1. This is like t equal to 1. And then the transitions go as follows. That is, if I'm at S0 state, at that first state, then no matter what I did, so basically whatever action I take, I'm always gonna land in S0 in the second step. This is like t equal to 2. While if I'm in the S1 state, there's only one particular action that's gonna land me into the S1 in the next step. Okay, that's called A1 star. And for whatever the action that's not here, that is not A1 star, so we just write this as A minus A1 star. So that is all the remaining action, I'm gonna go to the S0. So this is essentially, we're gonna duplicate this structure for T times, for H times. So when we at this state, whatever action I take, I'm gonna land in this state as well. And if I'm at this S1 state, And there's another action I take, a 2 star, that will land me here, and whatever other action I take will goes back to S0. So we essentially have this structure again and again till the very last step. T equal to 3, until at the very end, that is T equal to H. AH minus 1 star. And this is A subtract AH minus 1 star. So this is like the transition, and then we will set up the reward. Reward is basically everywhere reward is 0, and only if I reach this states, we will receive reward 1. S1 at T equal to H. Okay. So only at the very last step, if I go to S1, I got a reward 1. Otherwise, I always get a reward 0. This basically can be realized if you're really very strict about the reward, it has to be a state action function. Then basically it's saying that at the very last step, whatever action you take, you get a reward 1. Otherwise, you get reward 0. So we can see this transition has a very special structure. That is only if you take precisely A1 star, A2 star, A3 star. So this is basically the property of this combinatorial log, that we have optimal policy. So the optimal policy is pi h s0, which can be anything. It doesn't really matter. And the important thing is pi h s1 must be ah star. Okay. And this is the optimal policy. And when we choose this optimal policy, what you will get is the value of pi star. You will get is equal to 1. So this is the only case you will get 1 reward. That is, you precisely choose the action sequence, that is A1 star, A2 star, A3 star, till the very end. For whatever, every other sequence, you get a reward 0. So in that case, you basically has no signal. So you don't really know what is the optimal trajectory in that case. So let's talk about a random exploration, what a random exploration will do. So random exploration essentially try H as we said by different definition, we will try AH uniformly at random. So basically, this algorithm will not be very good until it kind of like try precisely this action sequence. Try this A1 star, A2 star, and till AH star. And until if you like basically sampled this precise sequence, then you will realize this is like the optimal policy, and then you kind of like you find the optimal policy. And like every time before that, it doesn't really know what is the optimal policy. So it's not very difficult to compute that the probability of precisely sample this action sequence is something like 1 over a to the h. So this is essentially the whole reason. That is basically we need at least a to the omega h samples. Or by samples here, we mean like trajectories. To find the optimal policy. Which you can even make an epsilon optimal policy, because here it's just the difference between 0 and 1. Why it's not a to the h?
Or why it's not like omega a to the h?
I think this is like a slightly weaker. I'm just claiming some weaker statement. A to the omega a to the h, you're essentially saying the exponent has to be h. But here I'm saying exponent can be h over 2 or something.
Oh.
Yeah. But basically, this is the key idea that is like reinforcement because it has temporal correlation. So if you do random exploration, especially for some long horizon, the probability of sample exactly one of the very good policies is like very, very low. So that's why if you just do some random exploration without using any like smart algorithm or like smart information, then essentially you will pay something exponential in the horizon, which is like people originally consider like a curse of horizon or something like that. And you can go back to convince yourself this algorithm is, this claim is essentially also true. So we're talking about this is like a purely random exploration, but you can also think about, you can do like a essentially random exploration. And then random exploration first, and then do like value iteration, or like you do something like Epsilon-greedy version of value iteration. Like by Epsilon-greedy means with 1 minus epsilon probability you do value iteration, with epsilon probability you do some random action. But the whole idea is the same. As long as you don't use any information to do this exploration, like as long as you try the action randomly, like Epsilon-greedy essentially with epsilon probability, you try action randomly. As long as you try action randomly, you will suffer from this like hard instance. Essentially, that will not work. Or it doesn't matter value iteration or Q-learning. So basically, this is also one of the very important distinction between theory and I would say like in practice, a lot of people just blindly use the epsilon-greedy algorithm. But you already see it's like epsilon-greedy is not a principled algorithm that can solve any challenging exploration scenario. At least even for tabular setting, this is like a bad algorithm. This can only deal with those games where like basically it doesn't really require any exploration. Like it cannot deal with this hard instance. They can only deal with probably some easy instance of MDP that does not require much exploration. So as a side note, it turns out like people did a lot of experiments on Atari games, and they actually show the epsilon-greedy seems like perform reasonably well compared to other sophisticated exploration algorithm. But later there are also some analysis basically says a large set of Atari games does not require like complicated exploration. Basically, you can just do random action and that still work. But what we hear is like we want to solve for all the MDP, so there are some like challenging setting, it won't work. And we'll talk about how to make it work. So essentially, we need some like a smarter algorithm to do exploration. Exploration is essentially collected data, and whenever we talk about exploration, people also talk about essentially the exploration versus exploitation trade-off. So it turns out the key idea in the reinforcement learning of handling the exploration is called optimism. So we'll actually introduce this most important idea. We'll introduce this most important idea in the next in this lecture and the next lecture. So if we really want to talk about the exploration and the exploitation trade-off, it's better we started with some like a simpler model, so that we can talk about what is the algorithm and what is phenomena there. So it turns out in the literature, there's a field which kind of studied this trade-off for a very long time. That is the multi-arm bandit. Essentially, the first model we introduced in this lecture. And this entire literature kind of like really focus on this trade-off. And optimism is a key idea which we borrow from. Optimism is a key idea we borrow from this literature. Let's still recall what is the multi-arm bandit case. That is, we have like a bandit machine with 8 different arms. 1, 2, till 8. The protocol of like a multi-arm bandit goes follows. That for T from 1 to capital T, the learner picks an arm. IT. IT is in like basically the action set, and then learner observe the stochastic reward. RIT. we noted this here, the reward being stochastic is important because we no longer have the transition. The previous argument in MDP, we can study deterministic reward is because usually transition is much harder to learn than the stochastic reward. But here, because we have no transition, so we have to, like, again, say the reward is stochastic. Okay. So we say have some normalization condition where we say I is always in 0 to 1. That is, the stochastic reward is always bounded in some 0 to 1. And we have some expected reward of I, expectation of I, that is a random reward I'm going to receive for i's arm is equal to little I. Okay. This is expected reward. So we'll talk about two slightly different goals, but both of them are like standard goals in this multi-arm bandit literature. First, let's first talk what is best arm. Best arm is just defined as I star is equal to argmax I of Ri. Essentially, this is the arm that achieved the highest expected reward, and this is the arm we eventually want to find. So there are two kinds of goals. The first goal, or sometimes we call it pack or sample complexity, or some sample complexity goal. We essentially only want to find the epsilon optimal arm. I hat, so that by defining the epsilon optimal arm, we say the expected reward of I hat need to be greater or equal to I star, the best arm, subtracted by epsilon. So we at most tolerate some epsilon difference. And sometimes we also okay with not only just identifying an arm, we can also okay with identifying a distribution D, epsilon optimal distribution D. So that the expectation of this reward I sampled from D is greater or equal to I star subtracted by epsilon. This is we also find. Even if you don't identify a single arm, but if you can say a distribution and we say in expectation, this is good. I'm also okay with this. And there is a second type of goal in multi-arm bandits, which you can think this is like a stronger objective, which we want to achieve low regret. Where the regret is defined as follows. Where the regret up to iteration t, this is the number of iteration t, is equal to the best reward you can achieve, t times I star. This is like the best expected reward you can achieve, and subtracted the expected reward you receive by picking your arm sequence. Okay. IT. So this is essentially the expected reward if always playing the optimal arm. And this is the expected reward to receive by the learner. And the regret is very intuitive by its name. Basically, it says if regret is very large, you have a lot of regret. If regret is small, then basically you don't regret much of not playing optimally. So I just want to say this, because we have normalization, reward is in 0 to 1. So the regret scaling is always like in 0 to t. So regret is never going to be greater than t. So basically, if you achieve some linear regret, and that's already like a trivial regret, that doesn't say anything. That's like very bad. So the non-trivial regret is like we want to say sublinear or like square root t or something like that. So we kind of noted the most important difference between Go 1 and Go 2. Go 1 essentially says player can play anything. As long as he or she eventually identified the epsilon optimal arm. It doesn't really care about in the middle, like what you are playing. You can play poorly, but as long as in the end you identify epsilon optimal arm, this is good. However, in the Go 2, you can think the second goal is like more difficult, because the learner or the player needs to find a good arm, which is similar to the best arm identification case, but also needs to do the play reasonably well. In most steps. So you cannot just play some like a terrible strategy in previous steps, and in the end you realize what is I star. In that case, you can like pay some order t regret, which is like not what you want. So you can think this is like what we want to do in exploration. And this is like what do we do in exploitation. So the goal of regret actually naturally reflects the trade-off between exploration versus exploitation. So in reinforcement learning, although so far we only talk about exploration, like we never talk about the regret, we're okay with like the sample capacity. But it turns out because there's like a sequential structure and we already talk about random exploration doesn't work. So it turns out the idea developed for this balancing exploration and exploitation, the optimism, actually is very useful in reinforcement learning. So that is in the multi-arm bandit, we will talk more about how we're going to balance exploration and exploitation and motivates the optimism. And then we will talk about how to apply the algorithm, the optimism principle to reinforcement learning.